Hello and welcome to my talk here at CCS2020. I hope you will enjoy it. So what I want to talk about today is something very important to complex system science. It's a combination of the discussion of relational structures that go beyond pure graph theory and also stochastic processes that are defined on this relational structure. So these are two fundamental questions from modeling, from mathematical modeling. So taking, having a structural part, a static part, and a dynamic part. The problem with graph theory is that it has only binary relationships to model with. So in many cases, as we will see, we need n relations. And the second problem is graph theory is not able to reflect multiscale problems. And multiscale problems, I do think, are actually everywhere in science. So this makes this talk indeed extremely important. So how do we actually start to model? I just want to say that in a few seconds. So what we always start with is an object set which contains all the elementary particles of our systems. So for example, in an epidemiological situation, that would be a certain population of individuals. And then in a second step, the dynamic step usually is that if you have this classification into types, something like, for example, chemical species, then you see how these different types interact with each other, populated by the elementary particles, which are then classified into these types. The problem is that in many cases, as I said, there are multiscale problems. In this case, pure typification into single flat types is not possible. You have to have hierarchical types. Hierarchical types will be types that contain other types from lower levels. So for example, in chemistry, you will have something like a molecule which is can be very complex, and it contains submolecules of which it is composed of. These would be variables of lower order, and then it has even, smaller and smaller molecules up to the atom level, and then all the different molecules that are of this very complex type will have a certain amount of atoms from the basic object set. So this should motivate you why you need hierarchical types, and they are based on discrete levels here. So you have here the assumption that you have m discrete types in the levels in the hierarchy. You have to ask later how many objects of a certain hierarchical type are in a certain compartment. Let's say, for example, in this one. So if this would be the same example from chemistry, this could be, for example, a molecule which has 4 different types of chemical species, and then it can be composed of different molecules having different amounts of chemical species, and so and in the end, all the atoms in the universe will be present here in this basic object set. And if you like to know how many there are, for example, composing this molecule with 4 different chemical species, you have to find a path from the lowest level of atoms up to this hierarchical level upstairs. So this is defined as a so-called hierarchical envelope, and if the object set is finite, then and countable, then you can exactly say how many types there are, how many basic objects there are in a certain hierarchical type. Let me say a little bit about the generalization of graph theory. what we have seen in the classification before will be a so-called hierarchical hypergraph. In order to understand what a hierarchical hypergraph is, we have first to understand what a bipartite graph is. A bipartite graph consists of two vertex sets, and if you have, for example, a type, so this would be a chemical species, then the other vertex set would be, for example, all the atoms here, and a link would just indicate that you are a member of this chemical species. So this can equivalently also be described by a hypergraph, because you can just draw so-called hyperlinks around all the about all the atoms of a certain type. And so the two structures are completely equivalent. Another relational structure that you can use for n relations are simplicial complexes, of course. This works as well, but also simplicial complexes can in this sense not cover multiscale relationships such as hierarchical types, where types are contained in other types further above in the hierarchy. For this to do, you have to introduce hierarchical hypergraph. Hierarchical hypergraph is something that is a generalization of a hypergraph. So it just adds more layers. So on top of the hypergraph, there is a hypergraph and so on. You can see that in this structure. So you start with elementary objects. Then you have a hypergraph of level 1, which consists of a hyperlink only containing basic objects. And then you gradually build it up. But this is, of course, a very confusing picture. So it's better to draw this as a M-partite graph, and this is mathematically actually exactly the same kind of thing. Here's the construction that shows or proves that the M-partite graph and the hierarchical hypergraph are mathematically equivalent. Now we go to stochastic processes. Here, this is like a chemical reaction, as you can see. So this is a rule which defines one event and how different hierarchical types are transformed one into the other one. So if this would be a classical chemical reaction, then you would not have here these outer sums, which go through the hierarchical levels. But here they are included, and so this, let's say, chemical reaction-based rule can actually cover this multi-scale relationship. So it can have transitions which are happening to the types, to the hierarchical types at different hierarchical levels at the same time when this event is triggered. So this gives you a little idea that you need to define updates. And the only update in the system we are considering here is the so-called Gillespie algorithm. So let me go there. The Gillespie algorithm is defined by two numbers. So here you have Gillespie himself, and the Gillespie algorithm is defined by having two random numbers. One of the random numbers defines you when the next event will happen. That is described by the rule I just presented. And the second number tells you which of the rules, you have of course many in a typical system, will be executed. And then, you know, one stochastic realization of the process looks like that. So this is an example of a simple epidemiological model. You see here one realization of a run. So let's go back to the talk. So here, this explains you that we have different updates, and I'm just considering here the so-called collision update, which one of them is the Gillespie algorithm. Now let's end the talk with my example, which should motivate you why you need both things. One is the relational structure going beyond graphs, so we will have hierarchical types. And the second thing is we will have to define reasonable processes on the hierarchical types. So a good example is epidemiology. I'm sure you all know the classical SIR model. So here you have an infection process in the first rule, which tells you that a susceptible individual plus an infected individual lead to an infection. So you get 2 infected individuals out of that. And you have also a possible recovery where an infected person becomes recovered. Yeah, becomes recovered. So now this is of course so far a system which is completely non-multiscale. So how does it become multiscale? It becomes multiscale by introducing locations into this epidemiological model. This is very important for COVID-19, for example. So we know that we are more infective at certain locations. So I want to go straight away here to this diagram. You see that you have here a population of individuals that are forming the basic ZO. They have 3 disease states as before, which are S, I, and R. But now here you have 4 levels of locations. And here the first level is describing closed spaces. The second level is describing buildings and infrastructure. The third level is villages, and the third level will be regions. And now in each of these locations an infection process can take place, but of course an infection itself will always be on the basic object level, so only human individuals can be infected. And if you follow exactly these modeling guidelines, then your multi-scale stochastic processes exactly becomes like that. So you have the classical SIR model, but here instead of having only flat types, we have here reversible types. So here my 12 minutes are over. I have to stop the clock. It would need a little bit more explanation now how such a model is running smoothly, but of course I have to skip that, and you should just be aware that here this is describing a process which is describing an infection process that has possibly a very, very complex location structure, and so the hierarchical types here are put to good use, I would say. And it's also a motivating example to see that such hierarchical classifications make absolutely sense. Another example I could do is from chemical reaction kinetics, of course, but I will have to skip that due to the lack of time. So thank you very much.